doing today? Any questions before we begin today? Okay. Just a reminder, the chapter 1 homework and quiz are due tonight. If you have any questions as you're finishing them up at any time, please email me. You can come by my office if I'm still here today. I'll be here till probably about 5-ish, wrapping up labs and stuff. And I will soon be posting the chapter 2 homework, which will not be due until week after next, because we're only just starting chapter 2. So I'm going to go ahead and put it up, and I believe I'm going to ahead and post it to chapter 2 notes. Check that actually. The school Wi-Fi is getting in and out, right? They've been messing up, and they've been having to fix it. They apparently have not fixed it correctly, based on all the emails and all the times that the access point goes down. Okay, yes, the chapter 2 notes are presently posted to the Brightspace page. If you'd like to go ahead and pull those up or follow along or have them on the screen, put them up here. We're going to start talking about them today. And chapter 2 is just a direct continuation of chapter 1. We've been talking about motion, and now we're going to start talking about what causes motion in the first place, which is force. So, well, that's it. One more time before we begin. Any questions? Okay, have them at any time. Please interrupt me. So, chapter 2 is going to be about Newton's laws and basic mechanics. Which I agree with. I've said more than once, Newton's laws is very, very important to the history of how modern physics was developed. Several hundred years, Newton's laws were the way that he used and calculated really the entire universe. We were able to use Newton's principles to map the movement of most every planet in the solar system, on top of most objects on planet Earth as well. You can use these to chart and understand about 99.9% of all force and motion in the universe, which is why hundreds of years later we're still learning about them. Newton himself, again, very important. He gave us the laws of motion. He gave us rules about momentum and kinetic energy. It has to do with classical mechanics. Mechanics meaning the basics of physical objects physically moving. Odds are it is somehow rooted in Newton's work. So, Newton is one of the most famous things Newton did was he wrote a lot of the original math for how we understand gravity. Obviously gravity as a phenomenon existed before Newton, but Newton famously did a lot of the math for how we presently understand it. But Newton also gave us what is now known as Newton's 3 laws of motion. Now, as I've said previously, are the laws I'm about to show you actual universal fact? No, they're just our best guess at understanding the universe. They started as Newton's hypotheses of motion. Lots of other scientists agreed with them. They became Newton's theories of motion. They're still mostly uncontested, which is why we call them laws, but they aren't perfect, and they can still be improved. That said, they're still important and still useful, and that's why we are learning them today. So these are the 3 laws written in order, and on top of the fact you have been interacting with these phenomena your whole life, you have also heard all of these said to you before. Sometimes the way that they're described or written might change, but you've definitely all heard all of these before. The first law, which we've talked about briefly, claims that an object at rest stays at rest, or an object in constant motion stays in constant motion unless acted upon by an outside force. So, there are several objects currently sitting across this desk in front of the room. Until some force outside of that object comes along and disturbs them, they're just going to stay there. It takes outside influence to make these objects move. Now, this law, the first law, has a name. In addition to it having a description, it also has a name. So the first law is known as the law of inertia. Now, who's heard the word inertia before? Okay, good. Who knows what it means? And that's okay. So you're to learn about it. So, inertia is defined as the property of matter that causes it to remain at rest or at constant velocity until acted upon by an outside force. This is the law of inertia because this is the definition of inertia. Objects that have mass will remain at rest or in constant motion until acted upon by an outside force. And we call that property of mass, that tendency to remain as it is, inertia. So the first law is the definition of inertia. All matter, all objects that are made of matter, protons, neutrons, electrons, are going to behave like this. And the tendency to do that is what we call inertia. So, every single object sitting on this desk right now, they're all made of mass, all made of atoms, protons, neutrons, electrons, and the inertia of these objects is telling them, keep doing what you're doing forever. Their own inherent inertial tendencies are to remain still until some outside force, like myself, comes along and tells them otherwise. Now, objects won't just remain still on their own, they can also remain moving in constant motion forever until acted upon by an outside force. Now, on planet Earth, there's not a whole lot of sources where you can observe an object moving at constant velocity indefinitely because we have a lot of outside forces interfering with our ability to do so. So, let's say, desk up a little bit. So let's say the object we are going to examine is this empty tape dispenser. I'm going to put it right here. I'm going to exert a force on it to accelerate it, and it's going to be moving at some speed. Once I let go of it, if there's no outside forces acting on it, it'll just keep drifting forever, right? But realistically, why doesn't that happen? One more time. The table creates friction, both very good. So on Earth's surface, we are constantly dealing with friction. If you are driving your car and you get up to 80 miles per hour, if you take your foot off of the gas pedal, it feels like your car will not remain at constant velocity. But that's because there are outside forces like friction and air resistance slowing you down. The best place to be able to see this phenomenon for an object to remain in constant motion until otherwise stopped is in space. There's very little gravity if you're very far away from planets. There's no air resistance. So an object thrown into the void of space will just keep going forever because there's nothing to stop it. It'll just keep drifting. You don't really feel it, but the planet you're on is constantly moving through space. We have Earth, and you on it, has a constant velocity traveling through space, and it's going to keep doing that until something stops it. Let's hope nothing does. So, That is the first law. That is the law of inertia. This is the definition of inertia. The second law is very simply just this formula. And this is a new formula, so I'm going to tell you what each term in it means and how we can use it. I'm going to go ahead and describe what's on the screen already. So, sigma F, so this is sum of all forces. So F is going to be our variable for force. We're going to start talking about force numerically now. Force is equal to mass times acceleration. And force is what causes acceleration in objects. A force, to give you the physics definition, force in physics is described as a push or a pull that or a pull that creates an acceleration in an object of mass. The definition of force is that it creates acceleration. Now, acceleration is the change in velocity. That means that force is responsible anytime something changes its speed or changes the direction of its speed. If you want to make something accelerate, if you want to make something change what it's doing, you need to exert a force on it. And you've been doing this your whole life. You do it when you move your limbs around. If your arm is here, but you want it to be here, you use your muscles to exert a force on the mass of your arm, and that causes your arm to accelerate and then slow down when it gets to where you want to be. Every time you've ever picked something up, opened the door, you're exerting a force on that mass, the mass of the object, causing it to accelerate. Now, the variable for force is a capital F, and on the board we have the line underneath. You might also see the line up top. What do those symbols mean about force? Okay, force has a direction. That means it's a vector. When you exert a force on something, that force has to point somewhere. You can't exert a force without a direction. That force has to be in some direction. So force is defined as a vector. And notice, force equals mass times acceleration. Mass is not a vector, because you can't have 10 grams north, but acceleration is a vector. So objects will always accelerate in the direction of the force. Both of these will have the same direction. If I exert a force north on something, it will accelerate north. So this scalar times this vector creates this vector, which points in the same direction as the acceleration. So force does have a direction, but it's the same as the acceleration. The variable is capital F, and we are going to measure force in units of newtons. Sir Isaac Newton was so important to our understanding of force in mechanics that we named the unit after him. So, whenever we measure force in this class, the unit is going to be in newtons. And newtons is pretty straightforwardly just shortened to capital N, like how grams is shortened to lowercase g. Now this is the metric unit of force, and it's not one we really use a whole lot of in the United States unless you are in physics. But what, off the top of your head, is an imperial unit for force? What is the unit of force we most commonly use in the U.S.? Meters is distance. Okay, so weight is a very specific force. You're right. Weight is the force of gravity. And what do we measure weight in? Pounds. So the imperial unit of force is pounds. So you've been measuring force your whole life, just not in this unit. There are scientists who measure the performance of athletes, like world record batters or world record boxers. The force of their swing or the force of their punches is, at least in the US, often measured in pounds. We could also measure it in newtons, as we're going to measure it in this class, but that the unit of pounds you've been using your whole life is a unit of force. So you can punch with a certain number of pounds. You can lift with a certain number of pounds. So, now what this formula means, force equals mass times acceleration. If you want something to begin accelerating, if you want an object with mass to begin accelerating, you need to exert a force on it. None of these things are going to move unless something exerts a force upon them. And when I do exert a force on these objects, they will begin accelerating at some rate. Now that acceleration only lasts for as long as the force is applied. If I marker down. If I swat this marker across the table, I'm only exerting the force for as long as my hand is touching the marker, which means it's only accelerating for as long as my hand is touching the marker. Once it leaves my hand, that's when it enters the point where it is moving at constant velocity until something stops it. Make sense? Another good example. If you haven't done lab this week yet, this is the marble cannon we're going to be using. The way that this cannon works is when you load a marble into it, where did I put that thing? Load the marble, prime it, and there's a spring inside the cannon that exerts a force on the marble. That force on the marble's mass causes it to accelerate as it is firing out of the barrel. But once the marble leaves the barrel, we consider its horizontal velocity to be constant. Once it's exited the barrel, the force from the spring is no longer there, it is no longer accelerating. So, same with most projectiles. If you want something to accelerate faster, you need to exert more force. Alternatively, you could just exert the same force on an object with smaller mass. The smaller the mass something has, the easier it is to make it accelerate. It takes less force. I took Taekwondo as a kid. I did it from about age 10 to about age until I finished high school. And my instructor, my Taekwondo instructor, is the one who actually first taught me about this formula. And the way that he taught me was, if you want to punch something harder, you need either to move your arm faster or you need a bigger fist, which he taught us to encourage us to basically punch faster, because there's no good way to just make your hand more massive. Okay, now the last piece of this formula we're going to talk about before we start using it today is that sigma on the front. The sum of all of the forces upon an object is equal to its mass times its acceleration. So, let's look at this so I can use the marker. There's tape dispenser sitting on my desk. What are the forces presently acting on it? Say again? Okay. The tape, right now, as it sits there on the desk, friction is not a bad suggestion. The desk is exerting a force on it right now. Technically, that force is not friction, because friction only comes when objects are moving or trying to move. Right now, that the tape dispenser is not trying to move, it is not actively moving, so technically there isn't friction from the desk, but the desk is definitely exerting a force. The desk is exerting a force on the tape dispenser. What I'm going to put on the board now is what's called a free body diagram, which is just, I'm going to draw a box that represents the tape dispenser, and I'm going to put arrows on it to indicate the force acting on it. So this tape dispenser is an object with mass, it has some amount of mass. The desk is exerting a force on it. What direction is that force going to be in? The desk is going to push up. Now, why would the desk push up on the tape dispenser? Gravity is pulling down on the tape dispenser. If the desk didn't push up on the dispenser would just plow through the table. It would just fall straight through it. So there are multiple forces presently acting on this tape dispenser. And yet, is that tape dispenser accelerating? No. The reason for that is the acceleration of an object is caused by the net force. So, sigma F can be said as sum, S-U-M, of all forces acting on an object, but I will occasionally also refer to it as net force. They both mean the same thing. The net anything is the sum of all of that thing. So net force, sum of all forces. Either way, either word you use to describe it, there's more than one force presently acting on that tape dispenser. And in order to find the acceleration of the tape dispenser, you need to add all those forces together and use that in the formula to find acceleration. Only the net force goes in there. And just guessing right now, what is the net force? What do all the forces add up to on that tape dispenser? 0. Right now, all the forces on that object are unbalanced. There are forces. We have gravity pointing down, so Fg, force of gravity. The desk is also exerting a force, which I am going to call the normal force. Get into that definition later, but to at least name it now, the force that the desk is exerting is called a normal force. So the desk is pushing back out. The net force on this object must be 0, which means that these two things must add up to 0. That means they are of equal magnitude but opposite direction. Any object at rest or moving at constant velocity, therefore it has an acceleration of 0, all of the forces acting upon that object have to add up to 0. This is the only way for an object to remain in homeostasis as it is. You either can have no forces on it, or all the forces have to balance. When you're driving your car and you turn on cruise control, there's a computer in your car that does its best to keep you moving at constant velocity, right? The whole point of cruise control is the car will keep moving forwards and I can take my foot off the gas pedal. When your cruise control is turned on, your car is going to try to move at constant velocity. That means all the forces on the car have to add up to 0. So there's friction trying to slow down the car, and the car's computer is using the engine to exert just enough force to cancel that friction out and keep you moving forwards at the constant velocity. So either staying still or constant velocity has to come from the forces adding up to 0. If the forces don't add up to 0, you get an acceleration. That's when you start speeding up, slowing down, changing direction. That's all the ins and outs of this formula, which we will start using in a moment. The last law, again, is one you definitely utilized before. For every action force, there's an equal and opposite reaction force. If you punch something, it's going to exert a force back on you, which is why you should not punch cinder blocks for one thing. I've seen people do some really reckless things, like there are certain athletes who are trained to break things with their hands. If you're not trained to, don't do so. Right now, I am exerting a force on the board. I am pushing into the board with my hand. The board is exerting a force back out into my hand. And that force is the only reason I'm not falling over right now. If I lower my arm, what's going to happen to me if I'm no longer touching the board? Yes. So, every single time one object exerts a force on a second object, the second object will exert a force back. You might not always be aware of it, but it is there. Whenever you pick something up and hold it in your hand, you exert a force upwards on it, but it's also going to press down into you. That's how you feel its weight. And the more mass it has, the more force you have to exert to lift it, the more force it exerts on you. That's why objects that are heavier feel heavier in your hand. And that is Newton's 3 laws of motion. We'll get more into detail about this one later. Next thing we're going to do is start using this formula, because I want to make sure you're okay with the math, to be able to start looking at your Chapter 2 homework. I've been talking for a minute though, so if anyone needs water or the restroom, now's a good time. I'm going to take a quick break. It's hot out today. Stay hydrated. Couple things in every physics class that I really enjoy when we get to talk about them, one of which being force, if for no other reason than the Star Wars puns can finally begin. So, now, any questions before we work our first force scenario? Okay, so we have an object. It is a 500-gram box. And there are, let's say that this box is in the middle of a four-way tug-of-war match. There are currently 4 forces acting on this box. Let's say this is like a bird's eye view and we're looking down from the top of this four-way tug-of-war match. These are the four forces acting upon this object, one in each of the cardinal directions. And the first thing that we are asked for is, what is the net force on this object? No, net force, total, okay. Net force, total force, all different ways of saying the same thing. So, this is a two-dimensional situation. You have a pair of forces operating in the vertical axis and a pair of forces operating in the horizontal axis. We still need to keep those two axes separately. If we're adding all these forces together, you cannot just add 250, 125, 200, and 100 all together, because they're all pointing in different directions. They're working against one another. You have to factor in direction and also axis. So, one step at a time, we're going to look at the x-axis first. There's two forces in the x-axis. So, total force in x. There's the 250 newtons to the right and the 200 newtons to the left. So, is the total force in the x-axis going to be 450? No. Why?
Would they go in opposite directions?
Opposite directions. Very good. They're working against one another. One of these has to be negative to represent that fact, and normally on our xy plane, because it was left to be negative, so I'll just change that sign. So the net force in the x-axis is just going to be 50 newtons. Meanwhile, in the y-axis, you've got 100 newtons up and 125 newtons down. That's going to give us a net force of 25 newtons down. So those are the net forces in each corresponding axis. And that, in my opinion, has completely answered the question. We have found the net force. It's a 2D net force, but we have found its x component and its y component. You could list net force as sort of a coordinate system pairing to show the magnitude in each axis. This net force points 50 in the x and negative 25 in the y. It is a 2D vector. You can use it. You can label it as a coordinate system like this, but you can list it like this. You can list them separately. We have answered the question. We have found the net force. The next thing we're asked is, what is the total acceleration of the object? So, we have two axes to our net force. That means we're going to have two axes to our net acceleration. So we're going to have to use our new formula twice, once for each axis. So sum of all forces in the x-axis will be equal to mass times the x acceleration. Mass is a scalar. There's not going to be an x mass and an x mass and a y mass. The mass will be the same across both. So our net x force on the x-axis is 50 newtons. The mass of the object is 500 grams. Now, there's an important rule about this formula that I have actually forgotten to mention until right now. My apologies. This formula demands that you use kilograms for mass, not grams. The reason for that is, which I will put over here next to the unit of newtons. 1 newton is defined as 1 kilogram times 1 meter per second squared. the use of kilograms is written into the definition of the unit of newtons. The reason that scientists did this is because if we used grams instead, all of our forces would be 1,000 times bigger. Or the number would be 1,000 times bigger if we used grams instead of kilograms. So I would go from weighing 100, okay, hang on, let me go. I weigh about 1 kilonewton. I weigh 1,000 newtons. If we used grams instead to define newtons, suddenly I would weigh 1 million newtons, which they're just big numbers. It's just to make all of our numbers smaller and more manageable. So the formula, F equals ma, demands that you use kilograms. That means we have to convert our 500 grams into kilograms before we can proceed. So how many kilograms is 500 grams? Very good. So I'm just going to make that 0.500. And then the last piece is AX. So we now solve for AX. What should that end up being? Been doing physics, so I've been using my calculator for so long. I was really bad at mental math, and I second guess every single calculation I do in my own head, which is bad considering I'm a physicist with a math minor. So keep your calculator, you will need it, but try not to become too reliant on it. You will always have access to it though, don't worry about that. Next we'll look at the y-axis. So our net Y force is negative 25 newtons. Our mass is still 0.5 kilograms. We solve for AY. And that should give us, within the y-axis, negative 50 meters per second squared. Keep in mind these are accelerations. As long as this force is applied, the object will begin accelerating along these axes, and their velocity will keep increasing until the force stops, or until it is otherwise canceled out. So we have found the x and y piece of the acceleration of this object. At that point, I would say that our answer is found. You could write this as x-axis 100, y-axis negative 50 meters per second squared. You can leave it in component form. Either answer is acceptable, however the best works in your work. It is just a two-dimensional acceleration. Now, with this information, and just looking at the numbers in the picture, if you were watching this match, this tug-of-war match, what direction would this, like, if you were just going to point in a direction, what direction would the box start moving in? To the right, correct, and what else? Down. So it would move somewhere in this direction. A little more right than down. It's accelerating faster in the x-axis than it is in the y-axis. So it would probably start moving like this. Does that make sense? All right, very good. So, very quick example. The calculations aren't too bad. Any questions about this before I start talking about one of the biggest forces you've ever interacted with, that is gravity? So any questions first? Okay, so We're going to end by talking about the force that, oh, does someone have a question?
Yeah, quick question. Wait,
Yeah.
does it matter which goes first on the equation, like for sigma x, like the 250 minus 200?
It does not really matter as long as the signs are correct. So if you define left as negative, you could list negative 200 plus 250, as long as your directions are correct.
Oh, okay, so like, it would be negative 200 because it's to the left.
Well, yes. Every single problem, you have to assume which direction is positive and which one is negative. For the sake of being consistent across all examples, I've been working under the assumption that up is always positive y and right is always positive x, to keep it similar to coordinate problems you worked in the past. That's the assumption that I have been working under for all of these problems. And it helps to write this in the corner of your questions sometimes, just to remind yourself which way is positive. But if you wanted to, you could just completely invert it and say this is positive x and this is positive y, in which case all of your signs would switch. As long as your answer is consistent to how you set up the question, I'll count it as correct. But just for consistency across every example, I'm going to work them from this assumption on the board. Okay? Now, from this assumption, that would make left negative, which is why the 200 has a negative sign on it. But commutative property says you could write it as negative 200 plus 250. It doesn't matter what order they're in as long as their sign is correct. So, me putting the 250 first is just, in my head, this is more efficient because you only have to write one operator sign if you do it this way. But again, either is fine, however you want. If you're just listing them based on the order you see them, this is correct. Does that answer the question? Okay. Anything else? Okay. So, it's time for a conversation about gravity and weight. So, is everyone okay if I erase this map? Okay. Now, the definition of weight is the force of gravity. So Earth's gravitational field will be exerting a force upon your mass, the matter in your body. Weight is the force of gravity. Since it's a force, you can measure it in newtons or pounds. They're both units of force. In physics equations, F with a subscript of g, this is not F times g, this is F with a little g living underneath it. So F with a subscript of g is the variable that we usually use, that we reserve for weight, because it is the force of gravity. So any formula that has F and a little g subscript, that represents numerically force of gravity. And you can calculate force of gravity using the same formula that we just learned, but specifically you're going to use the acceleration due to gravity in order to find the force of gravity. So, force of gravity is equal to an object's mass times g, and g is the variable that we reserve for the constant negative 9.8 meters per second squared, the acceleration due to gravity. So, this is the formula to find the weight of any object. And it is really the same formula as this, multiplying mass times acceleration. Now what this formula means is, Every object will have a different weight depending upon its mass. But on Earth's surface, every object is subjected to the same acceleration due to gravity. This is not weight. If I ask you for the weight of an object, this answer will never be the correct answer. The number, there's only one time the number might be 9.8, and that's if you were looking at a 1 kilogram object, because the force of gravity on a 1 kilogram object wouldn't be negative 9.8, but it would be newtons. So the weight of a 1 kilogram object would be negative 9.8 newtons, but this number will never be weight units of meters per second squared on it. The only object that will ever have a weight of negative 9.8 newtons is a 1 kilogram object. That's the only time this number will be used for a weight. All right? So all objects are pulled towards Earth with a different force of gravity, but they will all have the same acceleration due to gravity. And the thing about this force is, it will always be acting on an object, regardless of whether or not some other force is canceling it out. The tape dispenser on the desk, gravity is still pulling down on it, even though some other object is pushing up upon it. The net force is 0, but its weight still exists. Make sense? That's why this formula does not have a sigma in front of it. The net force creates net acceleration, but m times g will always just be the weight, regardless of whatever else is happening to the object. Even if I'm exerting a force to hold this object up, its weight still exists. It's still equal to its mass times gravity. I'm just exerting a second different force equal and opposite to it to keep it up. Any questions about these distinctions before I break for today? Okay. We've reached the end of the lecture. So these notes are already on the right face page. I will be putting the chapter 2 homework completed shortly for you to be able to begin them. But chapter 1 homework completed are still produced tonight. You prioritize that for the next 18 hours. If you have any questions as you work them, please let me know immediately. All right? And I'll see you all tomorrow for the lecture. I see you at the lab. Yes.
You said 18 hours?
Sorry, 13 hours. Not only am I bad at mental math, I also have this problem where there's a number in my head and my mouth doesn't say right. If you ask me what time it is right now, I would know it's 11 a.m., but I might say 7 a.m. for no clear reason. Any other questions?
Yeah, you go at 1:30 or whatever. Yeah. You have to like, you stay here for 3 hours. I was just probably there too.
Okay, this thing drifted again.